Hello.
Welcome to
Hello.
this lesson on
This is a lesson on heating and cooling curves.
The purpose
A heating curve is a graph
that
shows how temperature changes when you add heat to a substance. And most heating curves have the same shape, regardless of the substance. So it could be water, it could be sulfur, it could be iron, it could be carbon dioxide, but the curves will have the same shape, and we can get some key information about the substance by reading various phases of matter. So the goal of this lesson is to have you understand the key features of heating curves and their opposites to cooling curves, so you can get that
understand words are
the
used
heating
as
curve shows what happens to temperature as you add energy to a substance, and the substance gets heated and melts, and is heated some more and boils,
So a
and
heating
heated
curve
some
is
more.
a graph that
So the
shows
substance is going to
how
go from
temperature
solid to
changes
liquid to gas
as you
over
add
the
heat
course of the heating,
to a
and
clear
a predictable
substance.
thing will happen to the
Typically, we're
temperature
starting
of
with a solid, and then
temperature is
taking
the
the solid
dependent
until it
variable.
melts,
We're measuring what happens to
liquid
temperature
until it
as
boils,
we intentionally add heat to the substance.
Cooling
Adding
curve
heat, or the amount of
just
heat
the
added,
opposite. It's a graph that
is
shows what happens
the
to the temperature of a substance
independent variable.
as the substance
Temperature
is
appears on the
cooled.
y-axis as the
Typically
dependent
there, we would be
variable.
starting with a
You can
gas,
measure
we cool
in
it,
degrees
it would condense
Celsius
to
or
form
in
a
Kelvin.
liquid, then we would cool the
You could
liquid,
also measure in
and it would
degrees
freeze to
Fahrenheit.
form a solid,
Not
and then we
typical.
would cool the 200 mLs
And
of liquid and
energy
pour it in
added
the
is the
x-axis will be
independent
energy
variable,
container.
and
So
you
for
will
a heating
measure the
curve, that
amount
will
of
be
energy
added
in
of the cube
metric
you can
units,
measure the heat
or
by
kilojoules,
which is the metric
or
unit of
sometimes in
energy,
chemistry we
or
still use
calories,
calories.
Erlenmeyer
A
flask, something
convenient
with a
unit
different
to
shape
use. The
than we see here in
y-axis
English.
is
It would
always
occupy
temperature,
that
but the
same for
x-axis
the cooling
could
curve,
actually be measured
it would still
with
have energy
time.
will be
If we knew
gas
that
molecules
heat was
instead of
being
added.
added
So
to the
we're taking
substance
energy
at
out
a
of the
constant
substance.
rate,
Watch
then
temperature
we
drop,
would be
watching
measuring
it go through
time,
the phase
10 seconds,
changes,
20 seconds,
where
30
it
seconds,
forms,
40
they can
seconds.
expand
And
to where
essentially that would be
they will
equivalent
condense,
to
compress,
some
so the gas
constant
goes to
amount of
liquid,
energy
and
for
then it
each
will freeze
10 second
at whatever
interval or
shape
whatever.
solid.
So as long as we knew that the
Solids
energy
have
was being added at a
fixed
constant
shape
rate,
and volume,
we could measure
liquids have
the
fixed
time
volume,
instead of
but
actually
not
measuring how
fixed
much
shape,
energy.
and
Sometimes
gases
that's
do not
easier.
have
And
fixed
sometimes you'll see
volume or
time on the
fixed shape. For the
x-axis.
heating curve, you're
Is what I'm
adding the
assuming you
energy,
already know.
so the
First
temperature will be
thing that you
rising,
should
or you would be breaking
know
bonds.
about
how the
particles that make up
a solid
always have
you're
the
adding
same shape.
and a
So
solid
if I make a heating
will be
curve,
made up of
it's always going to start off low, where the temperature is low. It's going to have
so for a heating
an
curve,
upward slant,
like sodium,
followed by a plateau region, followed by another upward slant,
if that substance
followed
is
by
energy,
another
like
plateau
water, any
region,
kind of energy
longer than
then
the
we
first
would
one,
typically call those
followed by
joules
another
or
upward slant.
kilojoules.
So this is a typical shape for a heating curve. It has these three segments that show an
atoms. If it's
upward increasing slope,
time listed
and
as
we
the
have these two plateaus,
as the
these two
particles of the
positions where
solid,
the temperature
particles of the
stops
liquid,
changing.
because
The
gas
temperature
assumption
stays
is
the
that
same
you
for
would
a
be
while.
removing energy at solid, liquid, and gas its
and if you're
removing
energy
at a
bonded
differently,
stop
the
changing for a
then you
while,
could measure the energy removed by measuring how long it takes.
images
to undergo all of these
changing for a while,
and 3 or 4
traditional
sometimes you'll
that
see or
is
states of matter that are
predictable
well understood and
for
commonly found on
heating
Earth.
energy.
We see again is that you would be removing the energy added
The
to the rate, a drop of
and
water, therefore
will
every
go
second
through
or
the
every
same
minute you would be
series
removing the
of
same
temperature
energy.
changes.
Water, so time is kind of a substitute for energy
while they are
vapor
being
in the
heated.
form of cloud.
So the shape of the curve
y-axis is always temperature.
We see
and the temperature could be measured in Kelvin or degrees Celsius.
Now,
in the
when I look at the curve, I should be able to tell what states of matter are present. So when the substance is at the low temperature, at the very beginning of the heating curve, the substance is generally in the solid
cooling curve shows how
and I
temperature
heat
changes
that
are most
solid
familiar
for a
with
while,
energy
and
is removed,
eventually going to
heating
get to
curve
a
shows
point
how
where
temperature
the
changes
molecules
as energy
are
is
vibrating
added.
so quickly
And
that they break their
will
bonds
always be
and
a
form a
dependent
liquid.
variable. It would
And
be on the
that's what's
y-axis.
happening at this
And
plateau.
additional information about
The
plasma will
solid will
always
be changing
some
to
additional information about
and after all of the solid has
it could be
changed into a
time
liquid,
as a
then
replacement
the
for energy
temperature will rise again. But that can only happen after all of the melting is done. So when all of the melting is done, there's no solid left, there's only liquid.
All right. So now,
and then the temperature will rise again for a while until you get to the point at which the liquid molecules are vibrating and rotating so violently that the rest of the bonds break. So now the liquid is going to change in slope,
and then
while the liquid changes into gas, the temperature is going to stop.
in order to talk about what the molecules are doing,
and then after all of the liquid has been converted to gas and there's no liquid left, then
in
the
temperature
of the gas
and then there's another flat
adding to it. The slanted portions of the curve, you just have one state of
graph
matter.
always
has
solid,
in a solid,
the molecules
are
arranged in a
regular flat portions of the curve have some pattern to their
at these 5 sections,
firmly in
place represent
they feel strong
molecular attraction states of matter changes that they would undergo
between these atoms and molecules
from this section of the curve from A to B.
You should be able to identify the states of matter that are present at each segment of the curve.
And then the molecules
are
clumped together,
so they can't be compressed further.
That solid
just
will be changing to liquid.
So solid converted to liquid.
Very
By the time we get to C, all of the solid is gone.
In a
So from C
the
to D, we just have liquid.
Only
forces of attraction. To E,
probably
should liquid is melting,
at
so we have
the B,
the liquid is
in a
boiling,
liquid, the
melting
attraction between the
and gas present.
melting
all of the liquid has boiled away, and we only have
raising the temperature again until you have all of the solid completely melted and turned
there are
to
fewer
liquid.
bonds.
The temperature will not change.
Adding
The
energy
molecules
to
of
these
liquid are
molecules.
present
Some of them
together,
but not
the
all
temperature
of them. As a
can
result,
only change
and so if the kinetic energy or possibly the potential energy
all of the liquid
molecules
they can move
is
going to
they can rotate
past
there
one
are
another.
portions of the curve where we can identify that kinetic energy is changing.
They
feel weaker portions of the curve
forces of attraction, they have fewer bonds,
there's more freedom of motion.
At point
Molecules of a liquid can rotate
is gone.
ways
Once
that
all the liquid is
the
gone,
temperature
gas
is
molecules
constant,
and the solid
you're going through some kind of a change of
vibrating
and so during
back and forth and back and forth and back and forth.
Whereas molecules of a liquid, they can do
from
that
point
vibrational
A to B, the temperature is rising.
Solids can do,
point C
but they can also
D,
temperature is
spinning.
That
from
rotation
C
gives
F,
them an additional
the temperature
type
is rising.
So when the solid is changing to liquid, the temperature
molecules
of a gas, the liquid changes to gas, the
very, very,
very
weak
present.
Forces of attraction
at
for one
these
another. They're so small
where the temperature stays constant to the kinetic energy
what's
of
the temperature when you've added this
theory
much
about temperature is directly
of
proportional to kinetic energy.
The molecules of a gas do not
letter alpha to represent
what's the temperature? You keep getting
so
the same
temperature is
number
probably not the case in reality, but
when the temperature is
very
not
temperature is directly proportional to kinetic energy. When the temperature is constant, kinetic energy is constant.
We ignore
that's how we find portions of the temperature
for that
kinetic energy is not
so if I work backwards from that
space where the temperature is rising,
what is that temperature?
Well,
that's the temperature I'm going to call the
some molecules might be bumping into one another. They're not really bonded.
So
since the temperature is
rising,
as we go from A to B,
and after all the solid is gone,
and
the temperature will rise.
The molecules of the gas that claim they're very far apart
this plateau
kinetic
where the
energy must
liquid
be
is
rising
changing
In
into
addition to
gas.
being able
and
to
so the
vibrate and
temperature is
rotate,
rising
the
as you
molecules
go
of a
See
from
what
liquid
value that
to molecules
has
of a gas
for
can
the
also have a
temperature.
type of
must be
motion
That
rising
that we
temperature
refer
would
to
be
as
called
places where
the
translation.
temperature
boiling.
goes
And this
up,
means that the
kinetic
molecules
When
can
energy
all
is
of the liquid has
correspondingly
so at
boiled
going up.
one
away,
moment the
Places where the
molecule is
temperature
temperature
here
start
is
and it
rising.
flat,
literally
But if you
moves
have
to a
constant, not
two
new
phases
position
changing,
together,
somewhere else.
kinetic energy
solid
It goes
changing to
through a
liquid or liquid
displacement.
changing to
So,
gas,
And
the
if
the
you're
molecules
asked
of
temperature
a
where is
liquid
the
and the
kinetic
molecules of a
energy
so that's
gas
a
can't
changing
really be
and
really,
together because
really
how,
there are
you
important
will
too
thing.
always
many
be
other
looking at the
molecules
Temperature
portion
in
of
their
the curve where the
is
range
temperature
until
is
molecules
changing.
of a
constant
And
gas
if the
have
temperature is
during
going
much
up,
higher
a
then
change of
kinetic
degree of
state.
energy will be
freedom
going up
than the
too.
molecules of a liquid. Because the molecules of a gas are so
And
far
when I can
apart, the
see
molecules
that
Potential
of a
energy
gas
constant
are
changes
temperature
don't
compressible.
correspond to temperature.
And
Potential
what
energy
that means
changes
is
on
the
that
correspond
graph
to the
can
freedom of
plateau,
motion.
move them
So the
then
closer
I can
potential
together
easily
by
energy
read
will
the
putting
temperature
them
correlate
that I
into
might
a
with
be
container
interested
with
in
the
some kind
as
of
molecules
physical
movable
have
wall.
properties of
more
that
So
substance.
freedom
if
to
So let's say
I
I
move.
don't
have a
know what this
container
substance is,
with a
so I
movable
heat
wall
it
like
to find
this,
out what its
So if
melting
I
point is,
have
and I heat
a
it to find out
gas
what its
with
boiling
the
point is.
ability to
down,
Now that
vibrate,
I know
rotate,
those two
and
physical
translate,
properties,
pushing
I might
it
be
has
down,
a
able to tell
lot
it
you
will
of
take
freedom
up
to
some
move.
of the
identify this
And so the
space
substance.
potential
So
between the
if
energy
I saw this
molecules.
of
graph
those
and
And
the
molecules
first
was
molecules
plateau was
higher
at
just
than the
0
need
and
potential
the
energy
second
of the
closer
liquid
plateau was at
together
molecules that can
100,
than they
only
I would
were
say,
vibrate and
oh, that's
rotate,
before.
but
water.
not
But they will
translate.
still be in
So
the
And the
gas phase.
potential energy of the
so
So
we
liquid
can
can
molecules is
compress
compress
higher
the
it with this.
than the
molecules.
potential energy of the
Molecules
solid
of
So
solid,
molecules that can
molecules
only
of
zero
liquid
vibrate.
are
and the
not
very
So
second
compressible
when we're
plateau
going
refers
happens at
through a
100.
phase
So the
change,
states
melting
when
at
point of this
bonds
substance
are
is 0
breaking,
and
forms
the
of
boiling
that's
point
gas.
of this
when
substance
So
is
they're
the
100.
100.
Oh, now I
potential
know that's
energy
water.
About as
is
close
going to
together
be
Just
as
going
so
you
up.
you
can
get
make a
When
heating curve
bonds
or
are
a cooling
breaking
curve
and
to
we get
identify it.
additional
So we
freedom
can't
to
smash them
move,
together further.
then that's giving the
Let's take a
molecules
moment to
more
look at a
potential energy.
simulation where
that's
we
And
can
so
two
actually
from
big
section
things. The
B,
overall
the
shape
from
of the
molecules
point
curve
B to
slanted
C,
upward,
and
the
the
flat,
potential
slanted
energy is
upward,
going up
flat,
because the
slanted
picture
bonds are
upward.
that
breaking.
And
When
what
you
um,
go
states
from
of
solid to
matter
allowing us to
liquid,
exist
see the
at
molecules are
each
vibration
of
and
getting
those
rotation of
5
the
greater freedom
sections?
of
gravitational
motion.
motion of the
First,
molecules.
And
solid,
from
So
then at the
section
this
first
is an
plateau,
B
image of
solid to
a
section
liquid,
B,
then
or
container
sorry,
upwards
from
again
that
point
just
B
to
to
has
liquid,
within
D,
it
and then
the
at the
potential
second
solid
energy is
plateau,
going up
oxygen.
there
liquid to
as
So you
well
gas,
can see over on the
because the
left,
then
liquid
I've just
molecules
hit
go
in
to
front of
gas, bonds
oxygen
are
and I've hit
breaking,
temperature
the button
and
move
gas
moving
solid.
left
molecules
to
have
right.
Up at
more
the top, you
freedom.
see a
As I said,
thermometer that
first
reads the
plateau.
It's
temperature,
probably worth
negative
noting at this point
242.
that the
This is
molecules are
below the freezing
gaining
point of
All right,
energy the
oxygen.
whole
another
So the
key
time.
oxygen is
feature.
in the
Energy is
solid
being
Kinetic
added
energy.
Oxygen
to the
is
The
diatomic,
molecules
kinetic
so each of
energy
the
of the
from
molecules has
some
a
molecule
external
link
source.
directly
to the
So
red
the
balls
proportional
of the
molecules are
temperature
being
temperature of the
heated in a
molecule.
test
And
tube
you
with
can
a
see
So
that in
beaker,
the
whenever the
solid,
or
the
the
temperature is
molecules are
molecules
being
rising,
have very
heated in
that
a
little
must
beaker
mean
with
the
a hot
kinetic
freedom
gun.
to
energy
move
is
The
around.
rising.
They
molecules are
And
can,
whenever
as
only
the
the
gaining
temperature
temperature is
is
energy
steady,
steady,
if
during
I
the heating
cool
process.
them,
This
that
is
must mean the
not
kinetic energy
an
is not
example
changing.
of
It is also
conservation of
steady.
see
energy
up at the
because
top,
So,
the
the temperature
molecules
is
are not an
where
dropping.
are their
Getting
isolated
kinetic
closer and
system.
energy
closer
The
to
changes
zero.
molecules
and
are
how is
receiving
it
energy from an
changing?
external
Absolute
source.
zero.
So,
And
If I
as the
include the hot
molecules are
plate
over
being
here,
and the
cooled,
water in the
go back to
you can
beaker,
that
see that
again.
they slow
then that
down.
could be
Their
considered an
their
isolated
From
system.
vibrational
A
Whatever energy
ability
is
to
lost by the
be
be
hot plate is
limited,
gained by the
more
kinetic
limited at the
molecule.
energy
colder
is
temperature.
changing.
So
And
what
how
But
is it
is
if
temperature
I'm
changing?
actually
only
measuring?
considering the
It's
And how do I
molecules,
measuring
know
the
not an
that?
kinetic
isolated
Because the
energy of the
system,
temperature
total
is
I
going
collection
up.
of
would not
molecules. So
assume
on
that
And that's
average, the
the
kinetic
happening
energy of
energy
for
these
is
molecules is
solid
traded
lower
off.
molecules.
The
So
energy
what
is
does
because
that
lower
mean?
only
they're
being
doing
gained.
Well,
energy.
they can
Which
I
only
means
guess
they
what
can
I'm
be
vibrate.
trying
more
to get at
If
steady.
you
is that
remember the
They could
last
only
video.
vibrate before.
on
So
the
They could
roller
if
only
the kinetic
vibrate
coaster,
energy is
now.
going
when the
up, I
marble
must be
went
They're
vibrating
downhill,
vibrating
less.
more
it
slowly.
lost potential
And as
energy,
then
but it's gaining
from
kinetic
C
to replace
rising,
it. That's
D
not
is
what's
the
happening
kinetic
here.
energy going
The
up
solid
again.
molecules
How do
are
I know
gaining
that?
kinetic
Because the
energy.
temperature
When
is
they
going
melt,
up.
they're
So
gaining
on
potential.
average,
The
going up,
liquid
more
molecules
kinetic
are
energy,
gaining
more
kinetic
going up.
energy.
So what's happening
When they
now?
boil,
I
they're
have
gaining
liquid
potential.
molecules.
And
They're
then the gas
vibrating and
molecules are
rotating
gaining kinetic
beyond
energy.
the melting
There's
point.
no trade-off.
Receive
It's not
vibrating
that when
of
you're
the
gaining kinetic, you're
faster
losing
as I
potential.
add this. So
You're
here I
gaining the
have
whole time
liquid.
because
And then
something
finally,
somewhere
from
else, the
so
hot
the
plate,
molecules
is
are still
losing the whole
connected. They
time.
feel some
So
forces of
overall, there's
attraction for
energy
one another.
conservation,
Kinetic
but not for the
energy is
molecules. The
rising and
molecules of
rotating.
whatever
How do I
substances
know that?
are
Sometimes the
gaining
molecules
some kind of
escape
energy
and get out
all
happening to
along
the
the way.
molecules. They are
if it
gas
slows down,
molecules,
it
so
can
they are
rejoin the
vibrating and
liquid phase.
rotating
Finally,
and
the
above
graph is
the
useful for
melting point.
reading some
If
key
I fairly
pieces
large
of
further,
information.
So I
the
can
molecules
read
will be
the melted point
vibrating
off
and
of the graph.
rotating
It's the
so
temperature
quickly
at which the
that they will
cells
break
break
the rest of their
So
bonds.
it's the
Kinetic
Y
energy,
value
all
that
of the bonds are
corresponds
broken and
with
the
the
molecules are
plateau
moving around
that I
separately
see
and
from
temperature's not
point
changing
B
with
to
high
point C.
degree of
So
motion.
this
And what about
temperature
then
would
I can
be the
see
melting.
that
The
obviously
temperature
we are in
shows
the
a
gas
plateau,
here. How
and
big kinetic
this
energy
temperature
is also
the
molecules are still
for the
vibrating, they're
second
still
plateau,
rotating, but now they
where
have the ability
boiling
to
is
move
occurring,
from one
is
location to
energy.
another
The
very,
boiling
very
temperature
easily because there are such
is
large spaces
so I can
around.
read those
In fact, they
pieces of
move
information off of the graph.
as the law of
This
inertia would
thing,
say they move. They
delta
move forward at constant
HFUS, is
speed until
called
they
the
bump
heat
into
of
something,
fusion.
and that changes
And
their
the heat of
direction. So
fusion
they move
is
forward until
the
they bump
amount
into
of
another
energy
molecule or until
that's
they bump into a
required
wall
to
or whatever.
melt something.
And I can
Fusion
do this
and
backward,
melting
more key features,
were
and then
synonymous
cooling the
terms,
molecules
but we
down.
don't typically
And
call
that
them
will slow them down as the
but it's still
temperature
kind of
drops,
stuck
the
to
kinetic
that
energy
delta H
drops.
there.
And
So
they
the
move
heat
more
of
from solid
fusion
to
is the
liquid.
amount of
Eventually,
energy
when
that's
I get
required
to
to
the
melt
point at which
everything.
they condense,
Now energy is
how
read
that
off of
depends.
the
Energy can't
x-point.
be created or
So the
destroyed.
amount of energy you need to melt this stuff is the amount of energy it takes to go from B
but the
to
temperature
C.
is not
So if I
rising
could read
colder, if I
that
go
value off
down
of the
below
graph,
negative 10,
subtracting
adding
these
is
two
going
x
into
points
breaking the bonds
to figure out the
instead.
difference between
And
them.
when
So
you
the
break
difference between
molecules
the energy
vibrate,
value when the
it
melting
gives them
starts and when the melting
more
ends,
greater ability to
move
if they are
around,
at higher
gives them
temperature,
delta
freedom,
H
less if they are at
of
liquid
fusion,
molecules have
the
I
more
get
freedom
to a
of
certain
fusion.
temperature where the bonds are
So
breaking,
then the heat of
from solid to
vaporization
liquid
is the
translates
one that
into
corresponds to
another
boiling.
temperature.
So
The rest
when
of the bonds
the
break
substance
is
starts to
proportional
boil
to
and when the substance stops boiling, the difference
Let's
in
quickly
energy
review the
between
phase
those
changes
two
that we
spoke
spoke
about
about last week when we were talking
more
about
freedom
physical and
symbolized
chemical
with
changes.
delta H
As I
V.
go from a solid to
So
a
the heat of
liquid, I
fusion
refer to that
is
as
typically a
melting.
smaller
Bonds are
number, so
breaking.
that
As
plateau
I go
is
from a
shorter
liquid to a
than the
gas, I
heat of
refer to that as
vaporization.
boiling.
Because
Again,
in order to
bonds are
melt
breaking.
something, you
I
just
have
need to
to
break
add
some of the bonds.
bonds.
Breaking some of the
Energy is
bonds
going into the
breaks
molecule,
down
giving them
the structure
additional
of the solid
freedom to
and
move around.
allows some
I go
molecules
from
to
solid
rotate and
directly to a
float
gas
from
state.
one
We
another.
refer to that
But
as
you don't have to
liquid.
break
They get
all of
more
the bonds to
group
do that. You don't even
those
have to break
three
most of the bonds to do that.
phase
You just have to break
changes
some of the bonds
together.
to do that.
We said
But
for
when
all
you want to
three
go
of
from liquid
those,
to gas, you have
bonds
to
are
break
breaking,
all of the rest of the
energy
bonds because
needed,
gas molecules are
added to
not
the
bonded
molecules.
together.
Since
And
heat is
so
going
if you want to
in,
break
we
all
refer
of
to
the
them
rest
as
of the bonds between
when
the liquid
you,
molecules,
here we
that's
see an
probably going to
image
take a lot more
that's
energy. So
showing the
generally the heat of
plasma state.
vaporization is a
The
number
plasma
that's
state
bigger
is
than the
like
heat
the
of
gas
fusion.
state in that
Change
the
the
particles have
molecules from
large
liquid
spaces
to
between
gas.
them and high
You can
degree
see
of
all of
energy.
this in
But the
the
particles are
order
charged. When we get to the plasma state, the
so
actual
cooling
atoms
curve
that started to break down
is
the
a graph
gas
that
is
shows
so
what happens to the
energetic
temperature of a
that the
substance
electrons are actually being stripped off of the atoms. And so as the electrons come off, what they leave behind is positive. So the larger orange or yellow pieces are positive ions, and we know that it's not changing over here are the negative electrons that have been stripped off of those positive ions. So a plasma is like a highly charged gas. Plasmas exist at really, really high temperatures. From A to B, temperatures like the surface of the sun, tens or hundreds of thousands degrees. We know that because the temperature is
always those same five segments, slanty, flat, slanty, flat,
potential and change
and it's either going to be headed in the upward direction, slanted, flat, slanted, flat, slanted, or it's going to be headed in the downward direction for a cooling curve.
Temperatures from
flat,
atoms,
slanted,
so the
flat,
kinetic
creating
energy is
ions.
So we call
Here
that
I'm
all
starting
along the
at a
graph,
high
we have
temperature.
some kind of
My
and
substance
when
is
we go backwards and
a
put
gas
the
to
electrons
start
on
off
the
with,
atoms,
and then
that is referred to
from point
as
A to B,
from A to
that
B
gas
gain
is
kinetic,
cooling
then
off.
from B to
The
C it's
kinetic energy
then from C to D it's kinetic
is
again,
dropping.
then from D to E it's
And
potential,
then at point
then from
B,
D to
it
F
starts to
changes
condense.
that are the
And the
reverse.
gas will
You need to
change
know that
endothermic
phase changes
slanted
when
portions
all
where
of the
temperature
gas
is
is
changed to
when
liquid,
kinetic is rising,
then
gas
there will be
molecules form
only
bonds,
liquid
bonds are breaking,
left
We call that condensation.
Liquid can
forming bonds.
While the gas is changing
finally,
to liquid,
and when liquid
bonds
we've
are
already
forming,
discussed the melting
and the
point, the
molecule is
boiling point,
losing
becoming
the
solid
ability
from the y-axis.
to
Again,
translate.
they are the
It's a type
y
of motion.
values
The
that
gas
correspond
losing some freedom of
directly
motion.
to the solid state.
Potential
The
energy.
lower of the two corresponds to the
when
all
all of the liquid
phase changes.
is formed,
all
none of the
show
gas is
bond
left over,
formation.
then
Energy
the liquid will cool down.
The other
from
two
the
values
when
that
I
you should be able to read out of the molecule in order to get them to form these bonds, they release energy when they form bonds.
Symbolize
Heat is coming out, so we refer to them
the
as
energy
just the
of
liquid
fusion
temperature
is
dropping, so the kinetic
another
energy
name
is
for
dropping, the
melting, right?
molecules are
I know
cooling
fusion
down.
doesn't sound like melting,
At
but
point
melting
D,
and fusion
very quickly,
were originally synonymous.
couple of little last minute things
delta
that
H
will
of
be
fusion,
done.
or
Liquid to gas.
and when
When a
freezing
liquid
happens,
changes
bonds
to a
form,
gas, we
the
actually have
potential
two names
energy
for
is
that
dropping.
energy is on the
And
x-axis,
then
evaporation,
point E,
and the
all
other
of it would
amount
have
of
been
boiling,
converted
and
to
you
solids
should
and
understand
solid
the difference
left,
between those two
and
things.
the temperature
It's
dropping
fairly
from
simple
point
and obvious, actually.
E
Evaporation
difference
occurs
for
for
molecules
molecules
temperature
at
is
the
dropping, the
surface.
kinetic energy is dropping.
length.
And this is just the
So
opposite of what
I
we
would
saw
read
here.
the
First it was
x-axis
kinetic
here,
energy up,
and I would
potential
read. So
energy
at the
up,
surface of the
here,
liquid,
up,
there are some
potential
molecules
energy
that
up,
have enough
in order
energy to
to get
escape
and
this
here we're
value.
seeing
They're
the
bonds
opposite.
with the rest
Kinetic
of the
energy
liquid.
down,
And
potential
if they
energy
break
down,
those
amount of
bonds and
energy down,
escape from the bulk of the liquid and get out into the gas state,
And then
float around
correspondingly,
separately,
the heat
we
of
refer to that
vaporization
as
is
evaporation.
the amount of
in the
energy
opposite
you need to
Evaporation
get something
occurs
to
at
boil.
matter,
any
So you would have
also
to
temperature,
read
opposite
as long
gas
as the
to
substance
liquid
is
to
a liquid.
solid
These two
instead of
spots.
solid to liquid to
Boiling,
gas.
on the other hand,
When
occurs
the kinetic
everywhere
energy
at
is
once.
changing,
It occurs
when the
throughout
temperature
the
is
liquid.
changing, how is
and
it
that
It doesn't
changing?
just
difference
occur
Well,
at the
temperature is
surface.
dropping, so kinetic
is
energy is
called the
dropping.
heat of
From point A to B,
vaporization.
from point C to D,
So
from
if I
point
have
E
a
to
bunch
F,
of molecules,
the heat of
vaporization is over
Generally
here
much
that have enough
larger than the
energy
heat
to
of
get
when
into
is
the
fusion. I have
gas
potential
made
energy
state,
shown it
they
that
changing?
will
way
When
form
bonds
a
are
bubble of
forming.
gas.
Where
But
does that happen?
remember
From
that
A
bubble,
to
because
C,
fusion
less
we're
is
seeing
the amount of
rise
energy
to the
to
condensation.
melt
top
something, and
and
melting
burst
something is
open
breaking the
and
bonds to go from
release
solid to
those
liquid.
gas
Bonds are
molecules.
So you don't
forming,
have
so
to
But
break
it
potential
all
doesn't
of
have
the
to
energy is
happen
going
at the
down.
surface. It can
some of the
happen
bonds.
anywhere in the
And then the
liquid.
structure
And
of
if
the
something
solids
is
at a really big rolling
destroyed
boil,
and
the liquid molecules
then
have
you
Bonds
have
are
bubbling
forming, so
forming
forming
past
all
each
over
other,
the
rolling
place
around
and
each
rising
other,
to the
and
And
so that
surface.
it can
finally, the
flow.
melting point
But
and the
in order to
boiling
go
point.
from liquid to
Well,
Well,
gas,
shouldn't
you
they be
have to
called
route
the
all
condensation
much of
point
the
and the
bond,
freezing point?
and that would
Sure,
typically
but
be
those are the
plasma
same
energy.
thing.
So
a
usually the
For
specific
heat of
example, if
temperature,
this were
vaporization is much
water,
bigger than the heat of
water
that we
fusion.
condenses
refer
at
to
100
as
because
So
water
the
boils at
boiling
100.
point.
Those are the
a
same
much
temperature.
larger or
So this is
longer
the boiling point.
plateau
Or the
from D to
condensation
E
point.
than
We
you
just
would
don't
from
typically
E to
use
C.
that phrase. We always call it the boiling point. Even for
Now, boiling point
condensation,
is
This
not actually
can
a
be seen
constant
down
value.
here
It's
in the
dependent on how much
opposite
pressure is pushing
down
down
or a
on the
cooling
liquid.
curve.
y-axis.
You don't
So
really
a
get no too
cooling
much
freezing
curve
like that.
would typically
Should
start
I call it the freezing
up
point or
here.
the melting
We
point?
would
It
see a
doesn't matter. Those are
decrease
the
in
same
energy,
thing. So
then
I
a
can say the
plateau,
freezing point of
then
water
another
is 0, the
decrease in
melting point of
energy,
water is 0.
then a
And
plateau, then
that
another
plateau will be
decrease
happening
in
at 0.
energy.
whereas
From
evaporation
What is
can
the
happen
heat
at any
fusion?
temperature.
The
You
amount
know, if I
of
leave a
energy
beaker of liquid
required
out
to
on my
melt
desk
something.
by just at 20
So
or 25
what
degrees
from
Celsius
position
will
room
I
B to
see
temperature,
on
position
I
this
might come
C,
back 3
we
days
would have
later
a
and the
this
gas
gas
graph
changing
will
changing
has
to a
evaporated
liquid.
the
at that
amount
which
of
we call
energy
lower
that I have
condensation.
to
The temperature
remove
may have
to
varied in the
freeze
room, and
something.
evaporation
So
was
whatever the
all
difference
along.
is
From
between
Boiling
these
occurs
points,
at
a
a
that
specific
would be
temperature
cooling off,
when all of a
heat
sudden
of
all of the
and
molecules
then
in
when
the
it
container
reaches
have
D,
enough energy to get
then
into
heat
the
of
gas.
freezing will
vaporization.
start. So the
Well,
liquid changes
that's
to
the opposite.
solid,
Or
Evaporation
that's
is
the
a
amount of
cooling
energy
process.
required to
and
It's a
then
cooling
boil
process
point
because
something.
the
E, the freezing
molecules
So
is
here,
left
start.
it's the amount
behind
of
So the
energy that I
have
have to
less
solids push
energy.
remove
down.
to condense something. So the
We see a
difference between
temperature
this point
drop
and this
from A
point,
to B,
this
so that means the
distance
kinetic
here
energy is
is the
going
heat
down.
of
We see
vaporization.
bonds
And
forming
so I
from
have a
B
quick
Get the
to
same
C,
simulation
information
of
for the
so
that.
that
cooling
means
curve.
potential
that we can get from the heating curve. So even though when we're heating it, we're getting the melting point and the boiling point,
temperature drop
and when
again.
we're cooling it, we're getting the condensation point and the freezing point. Those are correspondingly the same thing. Boiling point and condensation point are the same.
see the
and
temperature
freezing
hovering
point and
around
melting point are the same.
270
And that means
Heat of
the
vaporization
energy
There's a
that you
cover
get for
on
boiling
this, so
is
no
the same
dropping
as what
again.
we would call the heat
If we
of high
remove
gas
the cover,
condensation.
and some of the
And the
molecules
heat
at the
of
surface
fusion
get
or
out.
melting
We have
is the
corresponding
same as
graph
what we
that
would
is, we
call, I
can
guess,
see
the heat
over
of
here in this
freezing,
little purple box the
possibly
number of
heating pad would be
molecules
called,
left.
but
Instead of,
we don't
so I'm at
usually refer to
109,
those as
kinetic energy
107.
up.
So even
Then
mass
molecules are
condensation, we
leaving
call
the
it
liquid
vaporization.
Well, look, the molecules
because
that
you're
are left, they're
removing
the
the
slow
energy
ones,
instead of
because the
putting
fast
energy up.
ones are able to
And even when
escape.
it's freezing,
So with the
we'll call it
collection
heat
of
of fusion.
molecules that's left,
Just
I'm going to
that
stop
you're
the
removing
gas
the
for a
energy
second.
instead
With
of
the collection of molecules that's left is
potential
the
energy
set of
down.
molecules
Here's
that
an
didn't have enough
actual
energy to
graph
escape.
for
And in
water
general,
freezing.
their
Potential
average
energy
kinetic
down.
energy is much lower.
I like this
So
one
look what
because
happened to the
solid
temperature.
kinetic
The
energy.
temperature
here
of the
we see
solution
some
that's left over,
We
the
have the
temperature of the
same
liquid
5
that's
molecular
left over has
images in
dropped,
reverse,
which show
because all the
what the
high-speed
molecules are
molecules
like.
are the ones
matter,
that are left.
just
In
in
this
reverse.
Are the
section
ones
of
that
the curve, I
escape,
have
and
solid,
so the
which
average
here
kinetic energy of the
corresponding
leftover
gas
molecules is dropping,
solid.
Followed by
And in
because
this
all the
boiling.
section of the
high-speed are
curve, I have
cooling, so we
solid
have
changing to
so
liquid.
the average kinetic
Melting is
energy of the
happening.
molecules
We have
that
a
are
Here
left
we
over
see a
changes in
combination
kinetic
of
energy,
solid and
dropping.
liquid.
with
So you can see
temperature
that the
drops,
Temperature has
here
gone
kinetic
down
energy
from
goes
all of the
down.
liquid has
70
Last
on
time
to
been
kinetic
warmed.
energy
There's
going
no
up.
solid
because the
left.
temperature
All
is
right,
going
so
Here
up.
I see this
evaporation
time kinetic
is a
energy
cooling
down,
process
here
because the
I see
leftover
liquid
changing
molecules
to
kind of
have
gas,
potential
less
energy
energy
changes.
as the
They're
high
happening
speed
at the
molecules
plateaus
changing
where
to
bonds
gas
are
forming
forming.
in a nice
And
potential
finally,
energy
when all
dropping,
of the liquid
but
is
if you
gone,
get out
I
of it
only
and
have
it's a
gas
bright
left.
chilly
so
day,
potential energy
see
the
just
evaporation
the
molecules are getting less and
So that's
water,
nice.
the
It gives
liquid
you a
water
good
off of
idea
the
of
surface
what
of our
is
skin
happening
is
to
going to
their
leave you
potential
feeling
energy is
colder
the
because the
molecules during the
molecules that are
be
left
able to be the
over
melting
have
point.
KE
a
is
lower
going
average
up.
lower
kinetic energy.
plateau.
KE
And
is
also,
going
the
up.
molecules are
melting point
stealing
and the
energy
freezing
from
point are the
you
same
so that
number.
they can get
So
out
it
into the
doesn't matter
gas
if you
phase
call it
if they're
melting point
taking
or
some of
freezing
your
point,
energy,
that's
you're
the
going to
same
feel
thing.
colder.
And this
Finally,
value, the value that corresponds to the Y value
I
of
can
the
read the
highest
melting
we
point
are
for
less
water
familiar with.
off of this
The boiling
graph.
plasma
Melting is happening
is
at
like
100.
the gaseous
Excuse me, at
state
0.
state particles are
Melting point
charged.
happening at
So
0.
So we can
examples
read
of
the melting
plasma
point
would
and the boiling
include
point off of this graph,
the air
though
around
I
a
what's
can
lightning
happening
read
is
strike.
backwards
condensation and
There's enough
freezing.
energy from that
Melting and
lightning
freezing
to
occur at
strip
higher
electrons
plateau.
off of
I
the
boiling and
see that
oxygen or nitrogen
curve
molecules and
is 100.
create a plasma inside a tube of a neon gas
Let's look
light.
at some real
The
graphs.
gas is highly energized and
I
highly
can read
charged.
off the
I'm sure
I
you've
like
seen
this
those
one
kind of
because
plasma
at the
the
top
balls
difference
here
where
it gives
between
you
this
an
number
idea
and this
of
number,
the
electrical
169
molecular
to 80.
states
coming
and
from the
molecular
center of the
motion.
gas in the
This is in
ball
calories.
is ionized. And here they're
The heat
showing
of vaporization
the
of water is
re-entry of
In this
the
area of the
space
curve
shuttle
we
I had
have
to
into
put
the
that
Earth's
scale on there.
atmosphere,
It did not
this
come
area
off
of the
behind
curve we
the
have
graph the
space
way it
liquid
shuttle.
and
was.
solid.
The
And since
gas
I know the
is
heat of
changed
vaporization of
to a
water is
liquid.
80,
A
and
plasma
Melting is
trail
excuse me, the
occurring.
heat of fusion of
Plasmas
water
occur
is
at
happening
super
around
high
this
temperatures.
temperature. So this
the
must
heat of
be the
fusion
I
of
know that
water
we
is
said that
80.
changes of state
And the heat of
were
vaporization of
physical
water is
changes
540.
and not chemical
So I put
changes.
in this little
But the
break
change to a
here to
plasma
show
would
that
not be
there must have been a
considered a
break in the
physical
graph
change.
there.
If I had water, for
And this
example,
distance is
and tried to raise
correspondingly
its temperature to
large
10,000
enough. It's
degrees
not
Celsius, it just would not
big
be
enough
water
to show
anymore. The water molecules with
540.
gas break down
So
into
the break
hydrogen and
is
oxygen molecules, and then the hydrogen and
boiling
oxygen
point
takes
molecules would break down into
540
hydrogen and
calories
oxygen
point of
to
atoms, and then the
boil
electrons would
1
start to come
gram
off of
of
those atoms.
water.
So by the time I
And
got
it
to this
takes
high
80
temperature,
calories
there's no way it's
to
water anymore.
melt
So that would
1
not be
gram
considered
of
a
water.
physical
So this
change.
graph is
And that's a little
1
confusing
gram.
because we say changes of
If
state
you
are physical
had
changes,
gas,
real
but if we
values
wanted
on
to
the
include
liquid
axis,
plasma as one of the four
that
states,
is
that gets a little
heat
bit
of
confusing.
fusion.
Boiling,
It's
that
this
could possibly
this
be
image,
true.
I see
And
the
the heat
heat
of
some liquid
vaporization
left,
was
but I
just
see
physical.
also the formation of gas
This
molecules.
is
And
what that
then
graph really
finally,
wants
if
you're interested
finally,
in some more
when
information
all
about
of the
plasmas,
liquid has boiled
or
away, I
this
just have
new
gas
strange
or
state of
200
matter
water
called a
vapor. All
Bose-Einstein
that
condensate,
present.
then check out
This section of the curve here, kinetic energy is
chem4kids.com.
going
I know
up.
that sounds here
Again,
stupid, but
kinetic energy
it actually is a really good
here
site,
again,
and I
kinetic
thought that
energy is
the
going up.
information that they
This
had
section of
about
the curve,
Bose-Einstein
that's the real
potential energy is pretty interesting, and there was a
second
quick
plateau,
video
so it's a lot longer.
on
section
that
of the
site
curve
as well,
to break
describing
all of those
Bose-Einstein
bonds
condensates
in
and
the
here
water
describing
molecule
plasmas.
the amount of energy
in order to change them to
what happens at very, very cold temperatures, that is billionths
Now, originally this
of a
graph did not
degree
have these
Kelvin,
values on it.
and
I
by that
added
what we're
those
saying is we're
because I know
just
what
barely
a fusion of water
above
is
absolute zero.
80 calories.
So 1
And
over
so
10
I
to the
wanted
9th
to
degree
make that
Kelvin.
difference 80 calories.
20
And since this
to
amount,
100.
Anyway, when you're at
about the
these
same
super,
size as
super
that
cold
I
temperatures,
assumed
the
that
atoms
first
are
jump was to 80 and the
almost
next
still.
to 100.
Melting point is at 0
There's
still.
so little
Over
kinetic
here,
energy left that the
there
protons,
is some
neutrons, and
issue with the
electrons of
graph
the atoms
scale,
are
so I
almost
added this
motionless.
little break
And
in the
apparently,
scale,
at
which
those
is
What if
cold
it's
what you
not
generally
water?
show
If it's a
when
different
the
substance?
scale changes.
The
You have to
atoms
have
I
enough
can
kind
room
of
to make it
read the
wide enough.
superimpose
information I
on
need.
one
The
another.
Because I
melting point on
know
this
that maybe the
substance, whatever it
vaporization
is
of water is
super
like
atoms,
140.
like a
boiling point
blob
of
the
this
length
substance,
of
whatever
that
it is
line
they
for
stop
the
being
boiling
heat
for
of
discrete and separate
vaporization is
atoms, and
30
they
minus
kind of
10,
turn into
so
one
20.
big
20
atom.
Sorry, that's the
I
heat.
know I'm
So
not explaining
that
it
second
very
plateau
succinctly,
takes
but
them a lot
check out that
longer.
video. It's kind of interesting.
So 20,
So I
very good.
look at
made
the
numbers on the bottom
A
such
review
that
of states of
940
matter and
minus
hopefully some new
400 is the
information
here
for
difference
you
between
about what the
where the
molecules
boiling
are
you would
doing,
see
how
the
they're
and where the
moving,
boiling
how
starts
they're connected to
heat
each
of
other.
vaporization,
540. This is in
and that would be
calories.
80 minus 50.
And then after, again, all of the
30
liquid has boiled away,
kilojoules.
the
So you can get the
energy that you add
information that
after
you
that will
need
go into
from
increasing the kinetic energy
a
of
graph
the
of this type, a
water
heating
vapor.
curve.
This is
Here's a
an
cooling
actual
curve.
picture of what that
So
graph
here
should
I
look like.
have
And you see that
gas
the melting point happens at
and
0
gas
and the
changing
boiling
to
point is
liquid
happening
and
at
then liquid
100. And you see
and
that
then liquid
this
changing to
difference
solid and then
is
solid.
80. And you see
And I
that
can
this
read
difference
the point at which the gas condenses is 218. I call that the boiling
from
point.
740
The
minus
temperature at
200
which
is
the
540.
liquid
So this is a more
freezes,
realistic
you could call the
picture
freezing
of
point
what
or the
the
melting point.
heating curve looks like for
We don't
water.
generally use the term
And you see that
condensation point. We
heat
use
of
boiling point for that
vaporization
number. But you'll often hear
line
freezing point and melting
is
point used to
a
describe the
lot
same number.
longer than the heat of
In
fusion.
this graph,
line.
the kinetic energy of the molecules is dropping. Then as they condense, the potential energy is dropping.
Both of these are for
the
water.
liquid, the kinetic
the image at
energy
the
is
top is
dropping.
nice because
And then
it
as
gives
they form
you this
bonds to
corresponding
freeze, the
image of what the
potential
molecules
energy
are
is
doing.
dropping.
And
And
the
then
image at the
as
bottom
the
is
solid cools off, the
more
kinetic
is
energy
a
is
more
dropping
quantitative
again.
view.
This is
It shows you
condensation
that
happening over here.
the shape of the curve the way it really should be
This plateau,
numerically.
and this is freezing happening over here at this plateau. On this graph, I can't read the heat of fusion or the heat of vaporization.
Here's a heating curve
because it's
some
not
other substance.
We're not
So
measuring
what would
the
you be
energy
expected
removed from
to
the
do?
substance
You
directly.
would be expected to be
We're
able to
assuming
read
that
this
energy is
graph.
being removed from
So
the
if I were to
substance
ask you
at a
questions such as
constant
what's
rate.
the melting
And so by
point
measuring
of this
time,
substance? Well,
we're
you would have to
substituting
read
that
over
for the heat
from
of
this
for the amount of
plateau,
energy
and
removed.
see that it's
But
60.
if I
What's
knew
the
how much
scale?
time
The
it took
temperature's in degrees
for the
Celsius.
substance to condense,
What if I asked
and
you
I
what
knew
is
the rate at
boiling
which
point
energy
of
was
this
being
substance?
removed,
Well,
I could
here's
get
the
the heat
boiling
of fusion from
plateau.
that.
So you would have to
And if I
read
knew
backwards
how much time
and
it
see
took to
that
freeze,
it's 120.
and I knew how much energy
Again, the
was being
y-axis is
removed
in
during that
degrees
time,
Celsius.
I could
These
find the heat
dashed
of
lines
vaporization.
are not part of the heating curve. They're just allowing you to read that temperature.
And you
They're trying to
can
make that clearer for you.
go in the opposite
What
direction
is the
as well.
heat of fusion?
Draw a
for this
cooling curve for a
substance?
substance.
It's the
All right, so I'm
difference
going to draw a
between where
cooling curve.
boiling starts and
So
where it
that
stops.
means that
So it's always
I have
final minus
temperature
initial. 30
in
minus
degrees
10
Celsius
is 20.
on my
What is
y-axis,
the
and I'm going to have
unit? I have
heat
to look at the units on the
removed
x-axis.
because it's a
Kilojoule.
cooling
20
curve on my
kilojoules of heat
x-axis.
has to be
Now
added
my
in
y-axis
order
is
to
in
melt
degrees
this
Celsius because
substance.
I can see
And
that in
then
the
to do
problem.
the heat of
What is my
vaporization,
x-axis?
I
It
have to
looks like
look at where
calories.
boiling
Okay, so my
starts
x-axis is
and
going
where
to be
it
measured in
stops. Starts
calories.
at 50, stops at 80. The difference between those is
30. Again, final
The
minus
graph
initial.
always has
So
the
I
same
have to
shape. This is a
add
cooling curve,
30
so it starts high
kilojoules of energy
and
in order to boil all of this substance. It's only 1 gram of substance, so it's not going to
slants downward, then
take that much
plateaus,
energy.
slants downward, then
If I asked you
plateaus,
to
and
write
slants
down where
downward.
kinetic energy was changing,
They want me to draw a cooling curve for a
could
substance with a
label
boiling point equal to
A,
90.
B,
I don't really need to
C,
make a
D,
scale. I just need to
E,
label that point
F,
90.
and you could
And
say kinetic
freezing point
energy
equal to
is
40.
rising
So
from
that
A
second plateau
B,
happens at 40.
from
Again, I
C
don't need to make a
to
scale.
D,
I just need to
and
label
from
what that
D
Y value is.
to F.
Or
you
it
could
has
write
a
it
heat
right
of
on the graph.
vaporization
Kinetic energy
equal
up.
to 100.
Kinetic energy
Heat of
up. Kinetic
vaporization
energy up. And if I asked you where is potential energy changing and how,
so the
well,
heat
you would
of
say potential
vaporization
energy is changing
is
at these plateaus.
100.
So potential energy
And I
is
kind of
going
anticipated that going
from
in.
B
I knew the second one should be
C,
shorter.
and from
So the
D
heat of fusion
to E.
here says
It's going
50.
up because bonds are breaking. If you don't want to separate it out that way, you can write it right on the graph. Potential energy up.
Identify places where the kinetic energy changes and how it changes.
This
so anytime there's a temperature
that you're
drop,
heating is not an
there's going to be a
isolated
kinetic
system.
energy drop.
So it is constantly
And
gaining
anytime
energy from
there's
some outside source, like a Bunsen burner or a hot plate. It
bonds
is not
forming, there's going to
an
be a
isolated
potential
system
energy
like a
drop.
marble on a
Identify
roller coaster.
places where potential
For a
energy
marble
changes
on the
and
roller
show how it
coaster,
changes.
when
So
the potential
bonds are
energy went
forming
down,
here.
the kinetic energy
So
went up,
potential
and vice
energy
versa.
is dropping.
But that's not what's happening to these molecules. Energy is being added to the molecules the entire time.
And then finally,
from some
it says
external
identify
source,
the
like
states
I said,
of
a
matter
Bunsen burner
present at
or a
each
hot plate.
portion.
And so
Things
you're
can get a
not
little
expecting
crowded,
when
so
kinetic energy goes up, that
that's
potential
why
goes down.
sometimes it's
Or when
helpful
potential
to
goes up, that
label
kinetic goes
with
down. That is
points
not happening.
A, B,
When
C,
kinetic goes
D,
up, nothing's
E,
happening to
F,
potential
and then you could
because bonds
say
are not breaking.
from A
And when
to B,
potential's going
you
up,
only have a
nothing's
solid,
happening to
and
kinetic
from B
because
to
temperature's
C,
not
you have
increasing.
solid changing.
So when the kinetic
sorry,
is up,
that
the
was my
potential is
heating curve.
constant.
From A to
And when the
B, I
kinetic,
have a
when
gas.
the potential
From
is
B
up,
to
the
C,
kinetic
I
is
have a gas that's condensing to liquid. From
You
Z
do
to
the same
D,
thing
C
with
to D, I have
cooling
a
curve.
liquid.
So I have from
And
A to
from
B,
D to
solid,
E, I have
C to
a
D,
liquid
a
changing to
liquid.
solid, so I have freezing.
Whoops, I'm sorry, that's wrong. From A to B, a gas. From C to D, a liquid. From E to
And
F,
from
a
E
solid.
to F,
And from B
I
to
just
C,
have
the
solid.
gas
All
is
of the
changing to
solid.
liquid. So that's condensation.
That's it. Very good.
And I can read the boiling point from the graph, 218. Could we call that the condensation point? Sure. It's typically called the boiling point, though. And then from D to E, we have liquid changing to solid. That's freezing. And this temperature is the freezing point. Could I also call it the melting point? Sure. If I had to read the heat of fusion and heat of vaporization, this one is tricky because I'm getting the time and not the heat released. So here we would have heat being removed from the substance. And so if I knew that it was, I don't know, 10 calories being removed per second or something, if I knew how much time this was, I could find out how much energy was being removed. That would be a negative value because heat is being removed from the substance. It would be the opposite of the heat of vaporization. It would be the negative. But that is the condensation point, and condensation matches up with boiling. So that's the delta H of vaporization. It's not just melting because it comes first. And then down here, we would see the liquid changing to solid. That's freezing. Freezing is analogous to melting or fusion. So this difference would help me get to the heat of fusion. I can't read the heat of fusion directly off the graph because it's a time. And I can't read the heat of vaporization directly off the graph because it's a time. But those values, the heat of fusion and the heat of vaporization, they're positive values. These values would be negative because it's energy being released. Okay, last thing. Draw a cooling curve for a substance with a boiling point equal to 90. All right, so I have a cooling curve. I have an x-axis, temperature, degrees Celsius. Sorry, that was the y-axis. I have an x-axis. This is a cooling curve, so heat is being removed. And I'm going to measure that heat in, let's see, it says 100 calories, 50 calories. So heat is removed. I'm going to be measuring that apparently in calories. The graph has 5 segments. This is a cooling curve, so it starts high. Oops. So decrease, flat, decrease, flat, decrease. Okay, and it says the boiling point is 90. I don't even have to put the whole scale on. I could just put 90 on. And the melting point, it tells me, is 40. I don't have to put the whole scale on. I can just put the melting point on. I should have made that flat. It wasn't flat all the way. And let's see. The heat of vaporization is 100 and the heat of fusion is 50. So I guess I should have made this one shorter by half, right? So this has to be 50 calories and this has to be 100 calories. And then it says identify places where the kinetic energy is changing, and that's where the temperature is dropping. So the kinetic energy is going down here, the kinetic energy is going down here, the kinetic energy is going down over here. And then it says identify places where the potential energy changes and show how it changes. Potential energy is going down. Potential energy is going down at the flat portions of the curve because bonds are forming. Identify the states of matter present at each portion of the curve. So here I have solid. Here I have solid changing. No, I keep making that mistake. I'm so sorry. Here I have gas. Here I have gas changing to liquid. Here I have liquid. Here I have liquid changing to solid. And here I have solid. All right, that's it for heating and cooling curves. Some key features. The shape, the states of matter are always in the same order. The phase changes. On a cooling curve, you'll see condensation followed by freezing. On a heating curve, you'll see melting followed by boiling. And you can identify key physical characteristics of the substance, the melting point and the boiling point. The melting point happens at the lower plateau. The boiling point is the Y value of the higher plateau. The heat of vaporization is the amount of energy it takes to boil the thing, or it's the amount of energy you get out when the stuff condenses. That's the difference between when it starts condensing and stops, or starts boiling and stops. And the heat of fusion, that's the amount of energy that it takes to melt something. And you can identify that on a heating curve by seeing when it starts to melt and when it stops to melt, or on a cooling curve by seeing when it starts to freeze and when it stops freezing. Very good. Thanks.